In this video, we're going to talk about an area of fluid flow problems that happens at the end of the problem-solving process where you've already got the energy and the power you needed for your pump. Now you need to figure out if your pump is going to work or not. And to do that, you have to calculate the net positive suction head. Net positive suction head means that you have suction coming in on the suction side. So you have lower pressure on the suction side than you have on the discharge side. But your pressure doesn't drop so low that you start cavitating, which can wreck your pump. So you need a certain amount of suction head, or the ability to actually pull your fluid through the process to the pump for your pump to work properly. So let's take a look at how this works. Alright, here's a sample problem that will let us calculate net positive suction head and see, alright, is this pump going to operate properly? We are pumping water out of a large storage reservoir at a certain flow rate. We know the temperature of the water. We know there's friction in the line. And we know that that pump has to run at a net positive suction head that's NPSH of at least 2.5 to work properly. If the net positive suction head drops below that value, then the pump's going to start cavitating and you have major problems. So we want to figure out, does it work properly if we put the pump 1.5 meters above the water level in the reservoir? First thing, as always, let's draw that diagram. So we have a tank right here, it's a reservoir, there's the water in it, and we're moving that water out with a pump right there. Alright, we have information about the water level in that reservoir, so we're going to call that point 1. And we know, because we're calculating net positive suction head, that we are interested in the suction side of the pump. So we call that point 2. Notice that there's nothing after this pump, and that's okay, because we stop caring about what happens after everything gets out of the pump. We are interested in figuring out if this pump can run, if it has enough suction to make it work. So we'll just leave the diagram as it is. That is fine for this problem. Next up, we need to write the equation for net positive suction head, so let's do that. There it is. So our net positive suction head is equal to several different terms involving pressure, height, and friction. Note that all of these terms are in meters. Net positive suction head is in meters too. They're all head terms, and so head refers to meters. Height. What that height is if you turned all of these terms into an equivalent height of water, the amount of force that the water exerts on the bottom of that column of water. That's what we're talking about with head. So that's why we convert all terms to meters, just so we can do an equivalent comparison of all terms. They all have the same units, so they can all be added and subtracted from each other. The pressure at point 1 is what donates the most to your net positive suction head. So that is helping push the fluid towards the pump. So that's divided by the fluid density and the gravitational constant. That's our first term. Z1 is our height term, and so notice that we are subtracting Z1. This is because if Z1 is below the pump has to work harder to get the fluid up to it. If Z1 is above the pump, then it's actually helping the pump run better. So then we'd have a positive Z1 term. H1 to 2, that is our friction losses, and so that's friction due to flow in the straight part of the pipe, that's due to flow through fittings. Anything else in the line that causes friction is part of our friction term, and yes, that term is in meters, and we'll take a look at how to solve for that in just a minute. The last term deals with the vapor pressure of our fluid, and so we have to overcome the vapor pressure. We have to be at a higher pressure so that the fluid stays in the liquid form. We do not want this fluid turning into vapor. Basically what happens is that if the pressure drops too low, all of a sudden the pressure is lower than the vapor pressure. That means the fluid can start boiling at that temperature. Yes, even if we are talking about 20 C in this particular line, if you drop the pressure too low, the liquid is going to start boiling. And that means cavitation, and that means a damaged pump. So we have to think about the vapor pressure when we're calculating net positive suction head. Taking a look at the terms we're given in the problem. We have the pressure at point 1 because we know the reservoir is open to the atmosphere, so that's atmospheric pressure. We know Z1 because we know the distance between the water level in the atmosphere and the pump. And finally, we know the vapor pressure and density. It's not given to us, but we know we've got water at 20 C, and we can just look those up in standard steam tables. We also have the friction losses. We don't have them directly, but we can calculate them. So you might think, well, what do we need to solve for? Because we have all of this stuff. Well, that net positive suction head we're given is actually not what we want to plug into the problem. It's what we need to compare the net positive suction head we solve for to, so we can figure out if the pump is working or not. To solve for our actual net positive suction head that we have in this line, first of all, we need to figure out our friction term. So let's get started on that. Here's our friction term. In this equation, CF is our friction coefficient, G is our gravitational constant, and U is our velocity. If we look up at our problem, we have volumetric flow rate, not velocity. So let's convert that to velocity. When we crunch through that, we get a velocity of 1.1 meters per second. So let's plug that back in to our formula for our friction head. To do that, we get that our friction head is equal to 0.185 meters. Now, if we look up our vapor pressure at 20 C in the steam tables, we are going to get a vapor pressure of 2,985 pascals. Note that that's in pascals, not kilopascals. The density of water at that temperature is equal to 995.7 kilograms per meter cubed. Again, note the SI units. So now we have all the information we need to solve for net positive suction head. So let's go ahead and do that. There you have it. Our net positive suction head is 8.38 meters. Let's compare it to the required, which is 2.5. So our actual net positive suction head is greater than our required. And since that's the case, we're okay. Our pump is going to work. So we're not going to get cavitation because we have more net positive suction head than we need. So the pump could actually be placed a bit higher and it would still run okay. If you want, as an extra exercise, you can calculate exactly what height you can place that pump at above the reservoir level and still have it work properly. So go ahead and try that out if you like another problem to solve. But either way, this is how you figure out net positive suction head. If you would like to solve for any term in the equation, you can also do that by just rearranging the equation, provided that you have the net positive suction head that you want. Note that we looked up some information in steam tables. That's typical for a lot of engineering problems. You may have information that is available in tables that you need that's not necessarily given in your problem statement. So if you run into an equation where you have multiple things missing, think, can I look up this information in a table? If so, then you may be able to solve the problem. If not, then you may have to make some assumptions. With this problem, we were able to look up the information in the table, solve for net positive suction head, and figure out that yes, our pump will in fact work in this scenario.